Thank you. Our next speaker is Professor Joel Marks. He's a professor of philosophy at the University of New Haven, and he will help us how to think about the topic of planetary defense. So, Joel, please take it away and introduce yourself. Tell us what you do. Are you online currently and can share your screen?
Can you see me? Can you hear me?
We can hear you, and if you can share your screen, that will be fabulous.
All right, let me do that now. Let's see here. This is always the hardest part, right? Figuring out how to share a screen. There.
Okay, yeah, I think that.
Does that look good?
Yep, that's it. We have it.
Okay, thank you very much. Thank you, Nahum, for inviting me, and Ken for setting all this up. Let's get right to it, because I know we started a bit late. So I'm talking about the nature of the threat. And you might say, well, what is a philosopher doing talking about the nature of the threat? This is a job for scientists and engineers. And I must say, I'm tremendously impressed by the job that has been done in, well, I would count it from 1980, the last 43 years, since the Alvarezes came up with a hypothesis of what caused the mass extinction 66 million years ago, including the extinction of the non-avian dinosaurs. Since that time, a number of people have taken very seriously the idea that something like this could happen again, and that we are actually in a position to prevent it. And of course, the people who are at the front lines there are the scientists and engineers. But I do believe that philosophers who take an interest in this subject have something to contribute, and I hope that will become apparent from my presentation today. Now, I'm particularly pleased that due attention is being given to comets with today's conference. We've heard talk mostly about asteroids when we talk about planetary defense, because most of the objects, you know, that are likely to hit us are asteroids. But comets are part of the mix as well, and this has been recognized since the very beginning. I mean, right after the 1980 paper published by Luis and Walter Alvarez, there were workshops of scientists and engineers, some of them called by NASA, to look into this. And they all took comets very seriously, as in some ways just as much of a threat as asteroids. So I'm going to focus on comets in my discussion, but also please understand that comets can serve as proxy for large potential impactors, because comets, that's to say the nuclei of comets, do tend to be fairly large. So they can serve as proxy also for large asteroids. And now we even have the new category of interstellar objects, which could be in that size range. Now, even in our lifetime, in our little teeny puny lifetime in the age of the universe, we have seen what comets can do. Of course, what we're recognizing today is the anniversary of Shoemaker-Levy 9's discovery, and its impact came a year later in 1994. You can see that pictured on the left. I was able to see that with my very own eyeballs through a telescope as it was happening. Certainly one of the most thrilling experiences of my life. But much more recently, just 9 years ago, showing in the picture to the right there. In the lower left, you see that tiny little fuzzy blue object, and in the upper right, that large halo is actually the light coming from Mars. And comet sighting spring narrowly missed hitting Mars. In fact, at first, it was believed it was going to hit Mars, but then when they refined the calculations and then when they actually observed it, it narrowly missed. It came within less than one Earth lunar distance from Earth to Mars. Extremely, extremely close. And that was a lot smaller than the object that wiped out the dinosaurs. But nonetheless, it would have been one of those objects that could have done regional damage if it had hit the Earth, even as large as wiping out, let's say, the population of a continent. So this is not just something that happened 66 million years ago. In our own lifetimes, comets have shown their mettle. And I would also like to point out that 1 week from today is the 253rd anniversary of the closest approach to Earth of a large comet in recorded history. This is Comet Levix, and this was a large one indeed, larger than 5 kilometers. In other words, about half the size of the object that wiped out the dinosaurs. And that object came within less than 6 lunar distances of the Earth, only 253 years ago. So again, we're not talking here about something that's just in the way distant past. This could happen at any time, as Nahum also pointed out. Nonetheless, comets, as I say, have kind of taken second place to asteroids in the current planetary defense consciousness. In fact, very often, if you read the literature closely, you'll see that the word asteroids often stands for asteroids and comets, just the way the word men used to stand for men and women. Nowadays, we say men and women. But in the old days, they would just say men. And nowadays, it's still the case that people will often just say asteroids when what they clearly mean is asteroids and comets. And furthermore, the term near-Earth object excludes the most hazardous comets of them all, the so-called long-period comets, comets which orbit the sun in periods of greater than 200 years. Now, this is very odd, isn't it? But I can prove to you that this is the case. Because if we go to the CNEOS website that Nahum was showing us before, and we go to the definition of the near-Earth object groups, we see that it says, in terms of orbital elements, NEOs are asteroids and comets with perihelion, that's to say distance from the sun, distance less than 1.3 AU, where 1 AU was the distance of the Earth from the sun, on average 93 million miles. Then it says, near-Earth comets are further restricted to include only short-period comets. Now, this is quite bizarre because a long period comet is just as likely to hit the Earth as a short period comet. And furthermore, it could do, well, it could wipe us out, in fact. I think the average diameter of a comet nuclei are the ones that we know about in recent history is something like 3 kilometers, but they can be much, much bigger than that. So this is very odd. I once asked Paul Chodas who was the director of CNEOS, how come they're excluded? And he gave me an explanation, which I can't say I can completely accept, and maybe I'm not quite understanding it, but I think his explanation had to do with the fact that it wouldn't make much sense to be doing a survey of long period comets because they only come one or two or few a year. And meanwhile, there are trillions of them, presumably in the Oort cloud, which is their source, maybe almost a light year away from the sun. And we're just not going to be able to do anything that makes sense as a survey of them. So we just don't, for that reason, count them as near-Earth objects. But if we're doing planetary defense, we cannot ignore them, because they can certainly be near Earth. They can collide with the Earth. For all we know, the object that collided with the Earth 66 million years ago with a comet, although I think current thinking is that that was probably an asteroid, but it might have been a comet. So what are the reasons for deprioritizing comets in planetary defense? Well, first of all, relatively few comets compared to asteroids reach the inner solar system where the Earth is located. And by the way, this slide may be the most important slide I'm showing today. Secondly, comets would typically be far more difficult to defend against for various reasons. That's to say then the typical asteroids. I mean, again, asteroids can be very large too, but if we're talking about the typical one to be near Earth and the typical comet to be near Earth, the comets tend to be large relative to the typical asteroid that is near the Earth. They tend to be fast moving because especially the long period ones coming from the Oort cloud because of Kepler's laws, or I think it's a third law, they're going much faster than an asteroid that would be approaching the Earth, the typical asteroid. They would give us a very short warning time. Typically, we don't discover a comet until it lights up. And it doesn't light up until it gets fairly close to the sun because the sun is heating the volatiles on its surface. And that's when we can more easily see it. And typically that happens when the comet is at about the distance of Jupiter's orbit. And a comet that would happen to be approaching the Earth that were at the distance of Jupiter's orbit could reach the Earth in as little as 9 months. And there's no way that we could defend ourselves against such a comet if we were starting from scratch to prepare the spacecraft. And I want to talk about that fact later. They also are difficult to defend against because they can approach from every part of the celestial sphere, not just the ecliptic. The ecliptic is the plane of the orbits of most of the objects in the solar system, the planets, most of the asteroids. But comets, especially again, the long period comets, can come from any direction because the Oort cloud from which they come is thought to be spherical, surrounding the sun in a sphere. So this is another extreme problem in terms of both the dynamics of trying to defend against them and also in terms of just observing them, detecting them to begin with. Also, they are subject to perturbations by outgassing and outdusting. Also, they are liable to fragmentation because of their composition of volatiles and ice. And of course, most notoriously, as we know, Comet Shoemaker-Levy 9 split into 21 comets. So, you know, some people in planetary defense are saying you might as well just throw up your hands. If a comet is heading our way, we're doomed. My idea is that when the going gets rough, tough, the tough get going. And I think this is an argument for becoming more concerned about comets in planetary defense, not an argument for being less concerned about them. We have also seen that, you know, again, talking about the reasons why asteroids are given more attention nowadays, is that even very small objects can do tremendous damage. And again, combine that with the idea that asteroids are much more numerous, gives you the sense of, yes, we do definitely, I would not disagree with this at all, we definitely need to give great attention to small asteroids in planetary defense. But my position is going to be that we must give comparable attention to large objects, especially comets as well. Now, again, who am I to talk about this, right? I'm not a scientist, I'm not an engineer, I'm a philosopher. Well, I'm not going to take issue with the facts. I leave that up to the scientists and the engineers, and I accept all the facts that they have been telling us. In fact, I wouldn't be involved in planetary defense if I didn't know about the facts that those marvelous scientists and engineers have revealed to us. Philosophers are more in the business of considering inferences that are drawn from facts, and also the assumptions on which facts are made. By the way, I don't want to suggest that scientists and engineers don't care about those things also. They certainly do. But philosophers specialize in these things in a way that is rather focused. And again, I'm hoping that by the end of my presentation, you'll understand the difference between how a philosopher approaches these problems and how a scientist and an engineer would typically do, simply because we have to be specialists. There's just so much time in the day. Another way to think about the philosopher's approach is that our stock in trade is not so much facts as logic and concepts. And in my presentation now, where I'm really going into the philosophical part, I'm going to focus on concepts mainly, okay? So, for example, do unicorns exist? No, right? I mean, the concept of a unicorn, it's a horse with a horn on its, with a single horn on its forehead, and it has magical powers? Oh, unicorns don't exist. Yes, unicorns do exist. That's to say, if we take the unicorn to mean the concept of an animal with a single horn on its forehead. So in an odd kind of way, concepts determine reality. And I mean to take this very seriously. Here's something closer to our concern with planetary defense, having to do with astronomy. Is Pluto a planet? Well, I was brought up to believe that it was. But oddly enough, in 2006, the International Astronomical Union, for quite reasonable reasons, decided to alter the definition or the concept of planet. And guess what? As a result, Pluto was no longer a planet. So this shows that the concept is mightier than the Death Star, because we did not need a Death Star to eliminate a planet from the solar system. We simply change the concept of planet, and that's it. No more 9 planets, 8 planets. And now I come to planetary defense. Is there a high risk of collision with a Chicxulub-size impactor? Chicxulub is the name of the region in the Yucatan where the object that wiped out the dinosaurs impacted 66 million years ago. It was about 10 kilometers in diameter. And so I'm asking, is there today a high risk of collision with an object like this? And again, as I mentioned before, I'm now slightly switching the subject from a focus on comets, strictly speaking, to comets as proxy for large objects for which we have a short notice of potential impact. And long period comets do remain the poster child of this type of object. Well, the answer, the current consensus, is no. Why? Well, here's the argument given. The chance of a Chicxulub-size impact in the next 100 years, let's say, even without a robust planetary defense, is minuscule, 0.00001, if I got the number of zeros right there. A very, very, very tiny probability of an object of that size colliding with the Earth. Premise 2, risk is probability. Here we have a concept, the concept of risk, and we're analyzing it or defining it as meaning probability. Therefore, the risk of a Chicxulub-size impact is very low. But I would answer the question, yes, this is my contention. Here is my argument. Again, I start with the same fact. I'm not going to dispute the facts. The chance of a Chicxulub-size impact in the next 100 years is tiny. But now I'm offering a different analysis of risk. Risk is probability times consequence. By consequence, I mean the damage that would be done by such a collision. And by the way, this happens to be the standard definition of risk. And in fact, even most of the risk theorists and even the people in planetary defense, in the engineers and scientists, recognize that this is the standard definition of risk. Premise 3, the consequence of a Chicxulub impact size has a virtually infinite negative value because we're talking about extinction. We're talking about the extinction of our species, or at least the destruction of human civilization. Well, premise 4, even a very low probability times a virtually infinite consequence is a virtually infinite value. Therefore, I would say the risk of a Chicxulub-size impact is very high. That is my argument. Now, a lot of people are going to object to this argument. They're going to say, all right, you win on semantics, all right? But look, let's face it, let's be real here. It's still such a minuscule probability of one of these objects hitting that, we just don't need to give it that much concern. I can't tell you how many people, including in NASA, including in high positions in NASA, I've heard say, literally, I don't lose sleep over this one, okay? So I'm going to look at another concept now, probability. I want to talk about the analysis of probability. One thing, probability is not always predictive. This is because probability is, in a significant sense, subjective. in philosophy speak, we use the word epistemic for that. But in other words, probability has to do with what we have reason to believe. It's not about what is actually the case. And let me show you what I mean by that. Suppose that the next Chicxulub impactor heading towards collision with Earth will be discovered tomorrow. Okay? Meaning we'd have about 9 months to do something about it, meaning we're doomed. All right? Nevertheless, based on what we know today, literally today, June 24th, the probability of our destruction by such an object is vanishingly small. Furthermore, the disconnect between our knowledge about reality is even more radical. Probability in the sense typically used in planetary defense has to do with the frequency of events. For example, saying once in 100 million years on average. It does not have to do with the occurrence of an event, even a present event. For example, on the very day that we are going to be wiped out and know it by a Chicxulub impactor, on that very day, it will still be the case that it's highly unlikely. Because even so, it still only happens once in 100 million years. All right? So the last words of the probabilist as that object is approaching, about to collide and wipe us out, will be, but this was so unlikely. In fact, we just heard somebody say that it was so unlikely that we had these two objects, on the same day, the Chelyabinsk and the other asteroid that was predicted to come close to it. It's so unlikely. Yeah, that's what we'll say. That's what we'll say. But I don't know that that's a very good planetary defense strategy. Another way of putting it is that when somebody says an event of this sort occurs only once every 100 million years, this does not mean like clockwork. Again, it means on average. And again, scientists and engineers know this very well. Mainly, I'm addressing policymakers, not the scientists and engineers who know all this very well. So, for example, when Chelyabinsk hit Russia, the Russian emergency minister, Vladimir Puchkov, was quoted as saying, "We thought that humanity would not have to face such an attack for another couple thousand years, but the opposite happened, and Russia was hit with a large-scale natural emergency." Now, this is a ridiculous statement, because it sounds like he's saying, well, it happens like an object of this size only hits the Earth every like 3,000 years, and it was only 1,000 years since the last time, so we had 2,000 years left to go. But that's not how it works. That's not how statistics work. It's just on average once every 1,000 years, but you could have two in the same year. So for me, the most salient consideration is this. We simply have no idea when the next Chicxulub impactor will arrive at our cosmic doorstep. It might not happen for another 100 million years. It might happen in 9 months. So this brings me to one final concept I want to talk about: planetary defense. The term was coined by Lindley Johnson, who is today an amazing person, by the way. I mean, he has made so much of this happen, along with so many other people, of course. But he is the person who actually coined the term planetary defense. And next year, we could celebrate the 30th anniversary of that, because it was in the same year that Shoemaker-Levy 9 hit Jupiter that he coined the term in a white paper that he wrote when he was a He was in the Air Force at the time, and he wrote this as a part of a very visionary study commissioned by the Air University at Maxwell Air Force Base in Alabama. This study was called Spacecast 220, when they wanted to consider, what threats should we be thinking about for the year 220, which for them was, 26 years in the future. But the military, of course, wants to be preparing to defend us way in advance. And it needs a lot of lead time. And Lindley was the one who thought to think about an extraterrestrial threat. And this is the abstract of his paper. Again, it's just, he was so amazingly visionary. This is a quotation now. Preparing for Planetary Defense, that's the title of his white paper, develops its theme by initially defining the threat, and that hence is the title of my talk today, and discussing the surveillance of potential impactors, which I think is a great term to use instead of saying asteroids and comets all the time. Let's just talk about potential impactors and their orbits. It then examines ways to counter the threat through various mitigation techniques. Finally, it discusses the benefits of a Department of Defense role in an international effort and provides some specific recommendations. Although not a traditional enemy, asteroids, and he left out the phrase "and comets," are not, although he talks about them in the chapter for sure. Asteroids and comets, nonetheless, are a threat that the DoD should evaluate and prepare to defend against. That's why planetary defense, well, that's where the term defense comes from in planetary defense. So I will now sum up and say, in national defense against a foreign adversary, we do not let our guard down for 1 second. Radar and other devices are scanning the horizon continuously for incoming missiles and with backups and redundancy in case of failures. Furthermore, we are prepared to respond massively to any detection at once. Now consider planetary defense. We have only incomplete and scattershot surveillance, and mostly without backups. And we got a real wake-up call when Arecibo collapsed recently. Furthermore, should an incoming impactor be discovered with relatively short warning, we have at present 0 response capability. It is time, therefore, I submit, to move beyond only research, limited surveys and demonstration missions, and begin also full-scale implementation of a comprehensive planetary defense as it was originally envisioned, namely on the model of national defense. So what is the nature of the threat that planetary defense confronts? My answer, it's an existential threat. And I personally had the experience to encounter the last time most species on Earth were wiped out by touching. I was touching with this very finger the KT boundary in Gubbio, Tuscany, Italy, which I visited after attending the Planetary Defense Conference in Frascati in 2015. Thank you very much.